Okay, so some of the physical or geometric implications of these one parameter Lie groups of transformations, or alternatively their corresponding vector fields, are the following. So let's stick to two variables for now, that means x and y. So a vector field x given by, say, d by dx plus 0 d by dy is essentially your translation in the x direction. So as a one parameter Lie group of transformations, here your x bar will be x plus your parameter, and the y bar remains y. Remember, x bar and y bar come from g star on xy. Then if you have x equal to your vector x, your vector field x equal to y d by dx minus x d by dy, this is rotation in the xy coordinates. And remember, this one was g star on xy being x bar y bar, where x bar was x cos g minus y sin g, and y bar was x cos g plus y sin g, or something in that direction. Another standard one that features that we come across quite often is scaling or reduction. So this is scaling up or scaling down. For example, if you have 2x d by dx, that will be scaling up in the x direction and then scaling down in the y direction because of the negative sign. But generally, we refer to this as dilation or scaling. Okay, and of course, when there's some time variable, there are some other physical consequences that come from physics. Okay, so these are the vector field versions of the one parameter Lie groups of transformations. Just to, of course, put this one in the context of the one parameter Lie group of transformations, x bar here will be x plus g times 2x. This is your xi times your parameter. The y bar would be equal to y plus g times minus y. Of course, this is up to first order. This one can be written in exponential form also. You can write this in exponential form if you went through the process we described earlier on. Okay, what we're going to do now is to discuss the following. That this one, keep in mind, is scaling, rather translation in one of the variables. In this case, translation in x. We will discuss the following, that using the chain rule for multivariables, every vector field, say in xy, or even more variables, x, y, z, say, can be transformed to another set of coordinates, say st, where in the other variables we may desire a specific form like translation. Okay, let me discuss this first of all in general, what I mean. So if you have x, y variables on this side, and you have a new set of coordinates, say s and t on that side, we are given a vector field or representing the tangent vectors of a one parameter Lie group of transformations x in here. This will be, of course, xi ddx plus eta ddy, and on this side your vector field will be, say, x bar. So we can transform a set of coordinates xy to st by looking at the transformation of the vector fields. It turns out that we can write x bar as the vector field x on s d by ds plus the vector field x on t d by dt. So this is what we would use to transform a vector field x to a vector field x bar, i.e. from variables xy to variables st. And usually we will want the transformation to be something convenient. And it turns out that we can transform a vector field x, which could be something very complex like rotation or scaling, to a simple translation in the st variables. So if we require that a translation, say, in the x to be, let's say x be transformed to x bar, but where x bar is translation in either s or t. So say we take translation in s. Then what do we have to solve? Then just looking at the transformation formula above, we would want that x of s be equal to 1 and x of t be equal to 0. So this little equation, or this set of equations, if there were 3 variables, of course there would be 3 such equations. These equations then are used to transform a vector field x to x bar, where x bar is very simply d by ds, i.e. that d by ds there. And let's do a rather simple example to demonstrate this. So in this example, we want to transform the scaling vector field, and let's suppose the scaling vector field is in the xy coordinates, something like 2x d by dx minus 1y d by dy. Transform that scaling to x bar equal to d by ds, which is translation in s. The transformations from the xy's to the st coordinates. So essentially we'll be solving these 2 sets of equations. We'll be solving for s and t using these 2 sets of equations. Okay. So first of all then, we will have x of s, we'll let it equal to 1. That should give us a form for s perhaps, i.e. if you operate the vector field x on s, you will get 2x ds dx minus y ds dy equal to 1. This again is the old first order linear differential equation, which can be written as a system of ODEs, which I referred to as the characteristic form previously. So this will be 2x over dx over 2x dy over minus y. And again, because we just have 2 variables, this we require 1 independent invariant, and you always require 1 dependent invariant. So ds is then over that one there. Okay, so the independent invariant will come from this differential equation here. If you separate variables, etc., etc., it's better to take the 2 to the right hand side, so you get 1 over x dx equals minus 2 over y dy. This will give us ln x. This will give us a minus 2 times ln y, or ln y squared, plus an integration constant, which I'm going to call ln of alpha. This alpha, or ln alpha, is the integration constant, giving us the independent invariant. It's clear that when you solve for alpha, you'll get alpha is equal to, take ln y squared to the right hand side, that's equal to xy squared. So this is your independent invariant. To find the dependent invariant, we will have to pair off ds over 1 with one of these. So perhaps we'll choose that one. So taking this pair to solve for the dependent invariant, you get minus 1 over y dy equals ds. Integrate both sides, you get minus ln y equals s. This time I'll put the integration constant, which is going to be the dependent invariant gamma, and that will give us that gamma is equal to s plus ln y. Gamma is the dependent invariant involving s, alpha is the independent invariant, i.e. gamma is an arbitrary function. The dependent invariant is an arbitrary function of all the independent invariants, in this case just alpha itself, i.e. gamma is s plus ln y, alpha is xy squared, so therefore we have s is given by minus ln y plus an arbitrary function of xy squared. Since curly f is an arbitrary function, we may choose f in this case to be conveniently the zero function, so we can choose s to be equal to minus the ln of y. Right, next we have to solve the second equation, and that is x of t equal to 0. That will give us the form of t. So now we have to solve for t from xt equals 0. This implies that 2x dt dx minus y dt dy this time equals 0, i.e. in characteristic form dx over 2x equals dy over minus y equals dt over 0. So as before, the independent invariant will come from that pair, and we get the same independent invariant as above, but let's call it alpha star. So alpha star is the independent invariant, which we get by integrating this differential equation. Right, so there's only one independent invariant because you only have x and y as your variables. From dt over 0, since dt is over 0, t itself is an invariant, but it's of course going to be a dependent invariant. So gamma is equal to t itself, gamma star, and gamma star is some arbitrary function of the independent invariant alpha star, which implies that t is any arbitrary function curly g of x, y squared. Right, so we will choose a form of t because curly g is an arbitrary function. So we will choose the curly g to be the identity function. So choose curly g to be identity, so t will be very simply xy squared. So with these choices of s and t, that means s equal to minus ln y and t equal to xy squared, we will be able to transform this scaling vector field, one parameter Lie group of transformation tangents in x and y, to translation in the st coordinates, i.e. translation in s. We can very easily do this for more than two variables like xyz or xyzw and so on.